So now let's look at problem number 2. It's very similar to problem number 1. We'll be solving this by the method of factorization, and here we are given, not actually given, I'm telling you that P and Q are primes. They are fixed primes, which means we can treat them as numbers. They are not variables. It's just like we are given say 5x plus 7y equals to 1. Instead of calling them or writing them explicitly what P and Q are, 5 or 7, we have just written P and Q, but they are fixed. So let's solve it. Solution 2, we have P upon x plus Q upon y 1. Let's cross multiply this first, and of course we'll be solving this by method of factorization. So we get something like this, and now I cross multiply it, we get Py plus Qx is equal to xy. Here we get, now in order to factorize this equation, which is equals to 0, I'm going to add PQ on both sides. So then this becomes PQ. So let's factorize this now. I'm going to take y common from these two terms. I get x minus p, and q common from here, so which gives me, it becomes x minus p multiplied by y minus q. Just like I told you earlier, we always want a number on the right hand side, and here we got a number. These are numbers. P and Q can be anything. We can take them to be, just like I said, 5 into 7. So 5 and 7 are numbers. So we are happy with it. Again, I'm telling you, these are to be treated as numbers, not variables. Okay, this time around we are a little lucky that in this problem we are only getting 2 primes. In a previous problem we got something like 2 brackets, and then we got, I think, 16, if I can remember correctly. It was 6 something, maybe it was 8, right? Yeah, it was 8. And 8 is not a product of 2 primes. 8 is a product of these. 2 is coming thrice, so therefore we had to take many cases: 1 and 8, 8 and 1, 4, 2, 2, 4. Yeah, but here I think this will make our life a little easy. Let's see how many cases we get. Let's make our table. X minus p, here y minus q. X minus p can be 1, this can be pq, this can be pq, this can be 1, this can be p, this can be q, this can be q, this can be p. So we are getting as many cases as we got earlier, but still it is better if we had, say, 3 primes, p, q, r. Then there would be many cases: 1 p, q, r, then p, q, r, 1, then we can take p, q, r, q, r, p, then q, p, r. So see, and then q, r, p, then we can also take r, p, q. You see, we're gonna get more cases as the primes increases on the right hand side. If we only had 1 prime, say we had x minus p, y minus q as single prime, say 7. So we only have 1 7 and 7 1, 2 cases. So less number of primes, the easier it becomes. So just let me erase it real quick. So we are happy with 2 primes here. Of course, if they were 1, we would be a little more happier, but we can manage with 2 primes. So this is our table, and we can again take that -1 minus q and more such cases. You do that on your own, taking minus signs. I'm only going to deal with plus signs here. And if in question it is given that we are to find positive integers which is if in the question it is given that x, y belongs to natural number. So then you wouldn't have to deal with those negative cases at all, because then suppose you take this. So if you take this case, this becomes y minus q is minus pq, but from here we getting y as negative. So this case is discarded. Similarly, all negative cases will be discarded. So for now, let's just take x and y belongs to natural numbers. So then we only have to deal with these 4 cases, and from here it's very simple now. One solution which you're getting is x is 1 plus p and y is pq plus q from our first case. This from here we get this solution, and from here we get p plus pq and 1 plus q. Similarly, you can calculate the other 2 cases as well. So this problem is done now. Now we'll look at problem number 6. Let's write. So here we are given x, y minus 7 whole square equals to x square plus y square. So immediately we can tell this is to be done, or a part of it, or maybe creating whole square method will be involved in this problem, because there are too many squares. Factorization can always be done as here is, this is a square, it can be treated as a square minus b square. So here we can apply factorization. So factorization and whole square both have a possibility here. So let's see what can we do. Now we are happy that all these terms are in whole squares. But what is that one thing that's not going in our way? That is, we don't have a number on the right hand side, or we can't get a number on the right hand side. So from this equation in this form is not of much use, or is not of much help to us. We can't deduct many things from here. Okay, so what do we want? We always want a number on the right hand side, which will help us immensely. A number on the right hand side with 2 terms in product, or 2 terms with whole square, or maybe something else too, but in this section we are dealing with these 2 cases. Other things can also be there. From there on we can do more calculation and come to some sort of answer. It's not like that these 2 methods which were written here, they are only if we are able to get an equation in that form we can be able to solve it. No, it's not like that. In many other cases we can also solve that. In many other cases it's also solvable. So now let's see how can we get a number on the right hand side. What I'm going to do here now is I'm going to expand this term now. So here I can write xy to the whole square plus 49 minus 14xy. Now I see that if I add 2xy here, this right hand side can become a whole square if I add 2xy here. Okay, so this thing will become right hand side will become a whole square. Okay, that's one thing that I can do. That could be helpful, but I also want a number to be on the right hand side. Okay, so let's see where do adding 2x y will take me. Okay, let's try to do that. Adding 2xy on both sides. This becomes x plus y whole square, and here this thing will become minus 12xy, and this thing will become 49. Now if you see, if I had 36 here, this thing will also become a whole square, and I'll have a number alone. We can bring it to the right hand side, and our what we wanted we would get by that. So let's try to bring 36 here, which can be brought easily. Let's take 36 out from here, put 36 here, and we'll be left with 13. This side becomes whole square. It will come out to be xy minus 6 plus 13. This way we've got two squares and a number alone. So from here on we can proceed to solve our problem. So from here on, we can proceed to solve our problem the same way how we did it earlier. So I'm just gonna write it like this: xy the whole square minus xy minus 6 to the whole square equals to 13, which gives me x plus y. I'm applying the formula of a square minus b square. Here I get xy minus 6, and this term will become x plus y plus xy minus 6, and I get 13. So now let's quickly make our table. 1, 13, 13, 1, and minus 1, minus 13, minus 13, minus 1. I'm only going to solve a first case, and the rest of the cases you can tackle them all on your own. So let's see where does first case takes us. X plus y minus xy plus 6 is 1, and x plus y plus xy minus 6 is 13. So here simply we have two equations. We have to solve them to get our x and y. Let's add them up first. We get 2x plus y by adding, let's call it 1, 2, 1 plus 2 gives us 2xy equals to 14. We get x plus y as 7, and 1 minus 2 gives us minus 2xy plus 12 equals to minus 12. So this gives us xy equals to 12. Now we have x plus y is 7 and xy is 12. So from here what can we do? We can simply use the method of substitution, substituting y as 12 upon x is 7. Now this will simply become a quadratic in S, which you can very easily solve. This becomes x is 12, x minus 4, x minus 3. So we get x is 4 comma 3, and if we take x as 4, we get y to be 3 and 4. So we have 4 comma 3 as one solution and 3 comma 4 as another solution. And if we solve our other cases similarly, we'll get more solutions. And if it is given that x and y are positive, belongs to natural number, then you'll see that we won't have to deal with these two cases. Only these two cases will do. So that completes problem number 6.